Going to give us, it's going to tell us about a really cool application of indistinguishable obfuscation into succinct arguments.
Okay, well, thanks for having me here. Today I want to talk about a line of research that I've been pursuing with David Wu on getting SNARGs from indistinguishability obfuscation. So let me first start off by talking about what succinct argument, non-interactive arguments, or SNARGs are. We can think of a prover that has some statement, X, that it's trying to convince the verifier is true or is in the language. And both the prover and the verifier will have access to a common reference string generated by some trusted setup process. And what the prover will do is it will run the proof algorithm to produce a proof pi. And this will be just sent over in one shot, one certificate of proof, to the verifier. And the verifier can run the verify algorithm to figure out whether it should accept or reject. And one important thing about this being non-interactive is that any number of verifiers can verify this one thing. There's no back and forth between them. Now, intuitively, we're going to want to have two properties from any such system. First of all, it should be sound. That is, a computationally bounded prover should not be able to convince the verifier of a false statement. Second, we want it to be short or succinct, which we'll think of as meaning that the proof size would be polynomial in just the security parameter, and we can think of it as being independent of the length of the statement or the length of the witness. All right? Okay, so let me give you a very coarse-grained breakout of how of the world of SNARGs in prior work. So one path I'm going to lump together is all works where let's say we use the random oracle heuristic or some type of knowledge assumption. And we can trace this back to Killian and McCallie in the early 90s, and there's been many, many, many works since then, actually popular in practice, for deploying these. But we also might want to ask ourselves, well, what if we want to do it from standard assumptions, right? And we don't want a knowledge assumption. We don't want to use the random oracle heuristic. And there's much less choice. The main work that I know of is this work with myself and Amit Sahai in 2014, which showed how to get SNARGs from indistinguishability obfuscation. And this work even technically looks a lot different than these other works up here. And a few years ago, we had this neat work put forth saying that we can get indistinguishability obfuscation from what they called well-founded assumptions. And if you put these two together, indeed, we can get SNARGs from something at least hopefully approaching standard assumptions. But one big caveat with this work is that, as in the title, it's non-adaptively secure. This means it's only secure, or at least only guaranteed to be secure, against an attacker that declares, I'm going after this statement, before seeing anything, before seeing the common reference string. And this can be problematic for two ways. First of all, it seems the right definition is the adaptive one. And we can actually imagine attackers that might be happy to, I'll use the word forge, falsify, forge, any number of a group of statements, but can't figure out which one it's actually able to do until seeing that common reference string, right? So we want to have this. And moreover, if you look at this work, it's we didn't just forget to do not adaptive security. It's actually pretty well intertwined with how the proof actually goes. Okay, so the question here is, can we get adaptive security? To me, it was interesting that it's been pretty much roughly 10 years since that 2014 paper. And certainly, I don't think this is one of these cases where it's for lack of wanting. I mean, SNARGs have been, I think, on people's minds over the last 10 years or so. And the answer is yes. And it was actually been working on it with a line of 3 different works. The first one was with myself and David from about a year ago, where we showed that indistinguishable obfuscation plus perfectly re-randomizable one-way functions can do it. And we can get these perfectly re-randomizable one-way functions from either like assumptions like discrete log or factoring. But noticeably absent here is a number theoretic assumption like learning with errors. And the reason it's not here is because of the perfect word. Okay, so then not too long after that, at Crypto of last year, we actually took care of this learning with error issue. And in the work with Mark Zhandry, we actually had a similar approach, but finished it off in a different way using very lossy one-way functions. And that was able to do it. But then the final question that I was interested in is, can we do what I would call a pure indistinguishability type approach, obfuscation? There's a term maybe I'm hoping to coin or or to get used after a while. So by pure I/O, I mean indistinguishability obfuscation plus one-way functions, all right? And so this we actually finished off, and this will appear at Crypto 2025. The talk I'm going to talk about today will be a little bit of a blend of 1 and 3. The first part of the talk was originated here, obviously, and will actually be common throughout all 3 of these works. So I'll present that part first. And then for the second part, you could finish it off. You could do the second part in 1 of 3 different ways. I'm going to show you the newest way of how to do that. All right? OK, and we'll see if my terminology of pure I/O catches on or not over time. OK, great. OK, so to understand things, let's first take a closer look at that 2014 work and see how it goes, and also see why it's actually, at first, seems to be stuck in the selective world, non-adaptive world. OK, my 2 tools are going to be, the first one is going to be indistinguishability obfuscation. I guess we're in day 3 of the workshop, so hopefully this is not a surprise in itself. So indistinguishability obfuscation says if an attacker gives me 2 programs that compute differently, but are functionally equivalent, right? So
there are a lot of slides that look very similar.
Oh, OK. Well, I did one in the first one, so I was doing it in 2014.
It's usually X squared minus Y squared.
Sorry?
They all use this program. Yeah.
They all use this?
They use X and Y instead of ABC.
Oh, OK. Well, I was giving this talk in 2014, so I'm going to argue that it was. Anyway, let's not worry about that. OK, so everyone is familiar with the distributive property by now, let's say. OK, so we're going to flip a coin, and I'm going to use that to decide which one of the 2 to obfuscate, and the attacker's job is to guess which one, and we're going to say its advantage is, it's secure if its advantage is negligibly close to 1/2, right? OK, second tool, this is also used in works using I/O, are punctuable pseudorandom functions. So a punctuable PRF is like a normal PRF. It's a keyed function, except for we have the ability to puncture it at one point x star, which means that the puncture point should intuitively work everywhere except for x star, right? So we have a key gen algorithm, which takes as input the input length, and the output length. It produces a key. Puncture algorithm will puncture that key and give the slightly less working version of it. And then there's going to be an evaluation algorithm, which will take a key, either the punctured one or the normal one, and evaluate it. And the 2 properties that we want to have are, first of all, puncture correctness. The punctured key and the master key should give you the same answer everywhere except for x star. And at x star, if I have the punctured key, I shouldn't be able to tell the actual evaluation from just a random value. OK? And by the way, if there's any questions, feel free to ask. OK, so let's take a look at how that 2014 SNARG works. The main idea behind it is going to be that essentially there'll be 2 programs, a prove program and a verify program. And to the prove program, I'm going to show it my statement and my witness, and it will give me what I'll call a signature. And the verify program will just say whether it works or not. So the first step is going to be that we generate one of these punctuable PRFs. The domain of the keyed function will be the statement length, and the output length will be security parameter. All right. The first program we're going to conceive of will be parameterized by the relation R and the key K. And it takes in 2 inputs, a statement X and a witness W. And if the relation doesn't hold, the program just rejects, right? If it does, what it's going to do is it's going to produce a PRF value. I'm going to call this a signature, and I'm going to also, just my own terminology here, and if someone produces a false one, I'll sometimes use the word forgery. So it produces a signature on it if it does hold. And then the second program is the verify proof program, and it simply takes in the statement and the proof pi. And if we ignore this little f for a second, it's going to run the punctuable PRF itself and compare it to pi. Right? Now, the only change from that is that it's going to actually, instead of comparing them directly, it's going to run a one-way function on each one first. All right. OK, now actually making this work is pretty easy. For the common reference string, we just obfuscate both programs and give that out as part of the common reference string. The prove program will be to run the obfuscated prove program, gets you pi, and the verify algorithm will just be to run the verify thing. Okay, and you can see and correctness follows almost immediately from correctness of obfuscation. Okay. All right. So the neat thing about one of the neat things about this system, I think, is that we can actually prove security on one slide. So we can do it pretty quickly. Here, what I'm going to do is do a hybrid proof of security, where in each successive game, I'm going to argue the attacker's advantage is negligibly close to the prior one. So hybrid 0 is going to be the non-adaptive game, where the attacker declares X star and wins if it creates one of these forgeries on it, if the program verifies. In hybrid 1, it's going to look very similar, but I'm going to change the gen proof program, where I'm going to use the punctured version of the key, right? And this will follow that these things will be really close by indistinguishability obfuscation security, right? So we're not going to use the distributive part of math this time. The reason that we can do this is since that for the attacker to win, it has to be a false statement. It has to be not in the language, which means that there's no way that this line should get executed, right? So therefore, if I cripple the PRF at just this point, it won't actually change the functionality. And that's so this is an important point here. The next thing, I'm going to also use IO security again, where I'm going to change the verify program. I'm going to puncture it. And this time, I'm going to do what I call hardwiring of the functionality. So for all x, so let's see that these two programs here and here are functionally equivalent. For all x not equal to x star, it literally does the same thing, right? And for x equals x star, it's actually going to do the same thing, except for instead of computing this, it's just going to hardwire in what it's comparing against. Hardwiring, so y star is equal to little small f of k of x star, but instead of computing it with the pure f, it's just going to have that value hardwired in. So these programs are functionally equivalent. Now for the last step, we have to use each primitive at least once probably. I'm going to change this to be a random value. And I can do that because the function is, the PRF is punctured there. So I'm going to change that to a random R. Okay? And the attacker's advantage by, my laser, okay. And here is close. But you can see if an attacker actually wins at this last game, we can show that it can invert a one-way function or find the preimage of a one-way function, right? Make sense? Okay, so that's the 2014 system. And you can see it's a pretty simple proof. Interesting fact, it wasn't meant to be a SNARG. We actually called it a NIZIC. Well, I mean, it is a NIZIC too. We weren't wrong, but we weren't actually focused on SNARGs at the time. And I think just afterwards, it just happened to turn out to be succinct proof, all right? And then you can see here, though, it is very tailored. Shouldn't say tailored. The proof of security goes hand in hand with non-adaptive security. I need to know when I'm producing during this proof when there's some joke I'm not in on, but.
Let me share. I'm saying usually in talks about SNARGs, there is a question from the audience: how do they get around the high waters? And my comment is that.
Okay. You know, it's okay. It's okay. Okay, we'll. I have some bonus slides at the end if we can get there. Okay, so all right. So you can see here, I really need to know where to embed the challenge. Okay, and when I make this program, I needed to know where to put X star ahead of time. All right. So the first, yeah.
Maybe a silly question, but like, so you have this one-way function check, and like, have that. You don't know how to argue for security. Or sorry, in the verify proof, you're like putting this little f in front of the pi, right? Like if you just had it check whether it equals the PRF, it's unclear how to prove security.
You could do some tricks. Like if I used an injective one-way function, I could actually add in the injective one-way function later on.
Oh, I see. In the analysis.
In the analysis, actually, we'll actually see a little bit of that happen later on. So I could have it in the analysis and not in the construction itself.
Gotcha. And then you can just do f of x equals pi. F
Yeah.
of k.
Yeah.
K.
Yeah. Actually, that's a little preview for the future, perhaps. Okay, so one question. So thanks. Good question. So one thing we might ask is a lot of times in when we talk about adaptive versus non-adaptive security, a lot of times there's, I guess you could call a cheating way to do this, right? Which is sub-exponential hardness, complexity leveraging, and we just essentially what I call inflate the security parameter, and it magically becomes adaptively secure. So we might ask first, before we try anything fancy, does this work, right? Okay, so just as a quick review, for polynomial hardness, we're going to think of all polynomial time attackers will have a most negligible advantage in winning. And then for sub-exponential hardness, we'll say that it's a little bit stronger, but I think still considered pretty standard. All polynomial time attackers will have advantage at most 2 to the negative lambda raised to the c times negligible. And here we think of c as a constant between 0 and 1. Yeah? Okay, so the way we typically will use something like this is that there'll be what I call an inflating step, where we start with our base security parameter, add n to it, and raise it to the 1 over c. And if c is less than 1, that's going to be making it bigger, right? So we have this new one, we make it bigger. And after we do the inflation hardness, polynomial time attackers will have advantage at most 2 to the negative n. This is something that might be useful later on, times negligible. And this turns out to be useful. We've actually seen it in other places before too, where it could allow me, let's say, to do a hybrid, but where I need an exponential 2 to the n hybrid steps. And we'll actually see this in a little bit. So that seems to be useful. And we might ask, well, if we just do this, does it give us security as it is? And the answer is yes and no. It actually does work. But when you inflate that security parameter, both the common reference string and the proof gets bigger. In particular, they will grow with n. And for the common reference string, at least by the rules of succinctness I'm playing, it's OK for it to get bigger. This kind of has to do with this old Zhandry-Ricks impossibility result here. But also, right now, my proof size gets bigger. It grows with n, and now it no longer counts as a SNARG. So there's certain types of problems when you do this, I won't say trivial, but when you do this inflating type, straightforward inflating step, it works like an identity-based encryption. If you have a selectively secure scheme, you can make it adaptively secure with sub-exponential hardness, right? Other things like SNARGs, you don't get this for free.
But what do we know without I/O about getting this semi-succinct notion of SNARGs?
Sorry, without I/O?
If you allow the proof to scale to be comparable to the input size, but not to the witness size, what assumptions can we construct?
I have to think. I think without the random oracles and stuff, I still think that's hard.
Even then, it's
yeah. So I think if you just do this, if you just do this, yeah, you don't get if you have short statements and longer witnesses, just doing this kind of brain dead thing will actually be okay for the SW thing. Okay, so at least if we want to keep it short in the statement length, this won't work, and we need to have new ideas. I think intuitively the problem is the attacker can use a forgery or create a false statement at any number of statements, huge number, close to 2 to the n statements, and we need to be ready to use any of them. Before, in the previous proof, we could only use it at just one. Now we need to be able to use it anywhere. Yeah, Rachel?
One thing I'm curious about is that among all the primitives, that PRF is one where you blow up the key size, but you don't have to blow up the output size.
Yeah, in general, think of a PRF. Like you could have, just for encryption, you could have a PRF with a 1-bit output.
Right, so,
Yeah.
so it wasn't very clear to me if you blow up the security parameter, why would it blow up the proof size?
Because the security of a PRF, when you blow it up, will grow with the key size.
Right. So
And it won't necessarily affect the output length of the PRF.
and the proof is just a PRF.
Sorry?
The proof is just a PRF output.
But the secure still depends on the one-way function.
Yeah.
And then-
It's the one-way function that gets you. Actually, if you look at the next slide, I think it'll kind of answer it a little bit.
But that's all in the CRS. It's not in the proof.
no, it's a pre-image of a one-way function, right? The proof is a pre-image of a one-way function.
Ah, okay, okay.
Yeah, okay. And in fact, let me show you it right here. Okay. Okay, so what we have here is if we have sub-exponential hardness and we do this inflating step, for the obfuscation, we're going to have separate security parameters after post-inflation for obfuscation, punctuable PRF, and one-way functions. So we can actually, we'll see a solution where we actually do this inflation with both the obfuscation and the punctuable PRF. This will make the obfuscated program size grow bigger. It will also make the punctuable PRF key, not output length, grow bigger. and this caused the CS to grow. But for the one-way function, if we were to use something like a one-way function again, we want to not inflate this one, just keep it the same. All right? And so what this means is that there's essentially some rules of the game that we have to abide by. And so for obfuscation and punctual PRFs, at least in something following this type of construction, we can be in the size of 2 to the n type loop, or number of hybrids, right? But anything like an external one-way function challenge cannot be there. Anything that would affect that. Yeah.
Maybe you already answered this question. But if you take the construction and remove f from the outside, just don't use f, is it insecure? It seems like it's kind of very critically used everywhere. It just is an attack. Is it not a snark?
I think we'll I'll move on to the next one, but I could introduce the one-way function, the injective one-way function. I think Raul asked something like that.
That completely understands the answer. But the answer to my question, binary answer, is it insecure? You don't know, or is it still secure?
It's secure if I use an injective one-way function.
But there's no one-way function, so I'm removing one-way function.
But you can remove.
I'm putting it back in after you remove it. So I'm introducing it in the proof. Or is there a way to analyze it without a one-way function? Maybe that I don't know. Let me leave it at that.
So maybe if you wanted like a designated verifier SNARG, so then the PR.
Yeah, there was actually another. There was another paper. I forgot. We'll actually even get to that later on. That actually made that observation as part of it. Okay, so yeah, no, actually I will hit on that a little bit later. Okay, so actually let me show you the let me just kind of go forward and show the adaptive construction, and then we can kind of see what's unknown after that. Okay, so our adaptive construction actually looks visually a good deal similar to the 2014 construction, but have some important differences. So here what we're going to do is actually have 2 copies of the key. So instead of just signing with one, there's going to be 2 possible keys that I could potentially sign with. And I'm also going to have a separate punctual PRF, which will tell me which one to use. So if I look at the program, it's going to look pretty similar to before, right? Taking the instance, taking the witness, reject if the relation doesn't hold. But here what I'm going to do is first run the PRF for selecting a bit, which one to use, and then I'm going to run the proof with case of B, where B is the bit done just from there. So the PRF will tell me which of the 2 keys to use, and then it will just give me the signature using that key. And my proof will now be a bit B, telling which of the 2 to use, along with Z. All right? The next thing is that there's going to be a verify program, which will have not the selection key, but just these 2 different keys for signing. And as input, we'll take an X and pi, and the proof will claim one of these 2 bits, and it will do a direct comparison against that. All right? Now, I know a lot of people are anxious to see this without the one-way function, and here, this is our big moment. So you just had to wait. Okay, so this is what it is here. All right? Okay. So improving security, I'm going to break it into 2 parts. For the first part, I'll just intentionally turn off the slides. For the first part, what I'm going to do is I'm going to establish a condition that the attacker will win. If it wins at all, it will win off path. And for this part, I'm going to care that the attacker is doing on false statements. And it's going to be the second part will be set up by the first one, and I won't actually care if statements are true or false. Once I establish this condition, I'm going to forget about if statements are true or false. Okay? So and this first part, like I said, came from that first of the 3 papers, and it's modulo little syntactical changes the same between all 3 of them. All right? Okay. So the first one, what I'm going to say is that the attacker wins off path. So if we think that the attacker produces a proof on a statement X, this is its forgery, and proof pi, this bit B that it has, we want it to be the case that it's the opposite of the bit the selection function would have chosen. Okay? And so what I want to argue to you here is if that attacker wins with probability epsilon, let's think of this as non-negligible in the game, then with about epsilon over 2, just lose a factor 1/2, it will do an off-path, what I'm calling it, this is off-path, do an off-path forgery. Okay? So I want to first establish this. Intuitively, here's the argument here. So we can think of there being true statements and false statements, things in the language, outside the language. And all the attacker's winning advantage must be, by definition, in the false statements, right? Okay. Now, moreover, the proof program is hopefully, it has that punctuable PRF in it, but that selection PRF key is what I'm interested in. It has it in it, but it shouldn't be exposing that bit on false statements, right? It's, maybe obfuscation hides that, hopefully. So what I want to do is I want to argue that it would be difficult for an attacker to always match its proof for what I'm calling forgery with the selected bit, so about half the time we could hope that it will be off, right? Now we need to be careful because there's an exponential number of false statements, perhaps, like close to 2 to the n. Okay, so here's the argument for why this is the case. This would be a little more of the detailed part here. So I'm gonna think of D as being the event that the attacker wins, and E is the attacker wins, but with that off-path bit, okay? So what we want is the probability of E getting, we want to establish that E, if D happens, we want E to happen, right? So I want to say that probability of E happening is about 1/2 times D. I can think of, if I break it down statement by statement, I think of DI as the attacker winning with statement I, and EI with statement I, and the bit being off path. And what I can do is this is just, if I can prove this, I get this. This is just due to the fact that the attacker can only win when it creates a proof of something not in the language, okay? And then to get this statement here, I just need to show that it holds for each individual I, but not just negligible. I want it to be 2 to the negative n times negligible, because I'm going to add together, let's say, up to 2 to the n of these. So that's why I really, so this is where like we actually will use sub-exponential hardness and inflation and all that stuff I talked about earlier. Okay, and this is where it's going to come in. So I want to show this for all I. Okay, let me give you a quick proof for one particular I, and you'll have to do it for all of them. So let's say DI is the probability the attacker wins with statement I. Okay, and I want to show that these events are, except for one point where I do a 1/2 jump, all these events should be 2 to the negative n times negligible close. Okay? Let's see here. So DI is you win with statement I, then I can consider an event where you win, but I puncture that key at I star. Again, the reason I can do this from indistinguishability obfuscation is because it's a false statement. If this were a true statement, things wouldn't work out, right? I should be using the fact that it's a false statement at some point, we would hope. Next, I'm going to do something a little funny. I'm going to, let's say B is the bit that the attacker forges with. I'm just going to choose a random value S and declare the attacker only wins if B is equal, I call it B star, if B star is equal to S. Okay, well now the advantage is going to, by definition, drop by 1/2 between these two. But just, you have a bit, I choose a random bit, I say if they're equal, you win, if you're not, you lose. Okay, that makes sense, right? And now I'm going to use punctuable PRF security. Instead of S being random, it's going to be the complement of that selection bit. Okay, so the advantage should be 2 to the n times negligible close by punctuable PRF security. And this is something where we have a very small output, like the key can get really big, but we can have a small output length, right? And then the last one would just remove the puncturing again, okay? Kind of like the first step. Okay, so this will establish it. Any questions on this? Make sense? Okay, oh, yeah.
I mean, I am not convinced that you would need exponential number of hybrids here. Can't you use instead constraint PRFs and just do kind of like one hybrid and have 1/2 loss?
You would need to have a complex constrained PRF.
Single key, just a single key constraint PRF.
Let me get back to that. I think you're going to need the 2 to the n.
You need to constrain the false statements. You can't check if the statements are false.
No, the constraint function itself depends upon the key k, the k cell.
No, but you need to do it for every false statement, right?
You need to check if the statement is false. You need to constrain.
You just need to do it for the, so I'm basically going to say that for the punctured one, it's just for kb, whenever b is equal to fk cell of x, for that one, the kb thing doesn't give me anything. So I'm just going to say
okay.
K1 into single.
So I'm going to maybe skip over this a little. I don't think you're going to get away without doing 2 to the n loss here. I think intuitively, there might be a different way of sort of getting at the same thing, but this one you're going to have to go through each single one and do it. Yeah.
Oh, no, you can finish what you're saying. Oh, I was going to ask a different question. So, I mean, I guess this is really a question about your parameter selection slide. But, so, I guess the CRS length is growing with n, and the proof length is not growing with n. Is that right?
That's important, yeah. Yeah, it's at lambda plus n to, let's say, the fifth or something like that.
And I guess there's no hope to get CRS length that only depends on lambda, or?
I don't want to say there's no hope, but it's beyond what I can do now. And there we can talk about separation results and a few slides past the end if we want to do that. Okay, cool. So we're gonna eat a 2 to the n hybrid here. So this is where the CRS comes into play. Okay, so at this point, what I established is that the attacker, if it wins at all, will win with doing what I call an off-path bit. And at this point, I'm not going to worry from now on whether that's for a true statement or a false statement, right? If the attacker happens to do it on a true statement, that's totally great. It just increases the probability. Okay, so this is what I call, I ripped off the movie a little bit here, if anyone's used to that. This is where we need to use the fact that we set up this off-path condition and let's say embed the challengers like everywhere. So no matter where the attacker creates a forgery, we will be able to use it. Okay, I think some people brought coffee into the room.
No drinks or food are allowed in this room, and there are signs everywhere. Could you please observe it? These chairs cost $3,000 to replace, and we've had to replace a few of them because people spill things on them. Okay, that's why the signs are there. Thanks. Sorry to interrupt.
Okay, no, I'm disappointed in everyone too. I'm just joking. Yeah. Okay. Okay. Anyway, sorry, I lost my train of thought now. Yeah, it's all like all my great joke. Well, now everyone thinks it's funny. Okay, let's go. Okay, so here's how I want things to work. Okay, so what here we're going to embed. What we want to do is embed an injective one-way function. So let's think of y star is equaling to f of r, where f is going to be an injective one-way function. We'll get to the difference between using a one-way function and an injective one-way function just a little bit later. And so let's say now we're okay with injective. And right now, here's how my verify program looks coming in, right? And what I want to do is make the following change to it. Again, with this condition, you only win if you're off path. Like from now on out in the STOC, that's the only thing that counts. So what we're going to do is we're going to behave the same way if you're on path. But if you're off path, the verification program will have a different way of deciding whether to accept. Instead of doing this check, it's going to take your input z, XOR it with the punctual P or F for case of B. Hopefully people can see I'm not in the way. And run the one-way function on it and compare it to y star. Okay? And if we manage to do this, remember the attacker can only, at this point, the attacker can only win if it's executing this line, right? This one no longer gets you a win. So if you can do this, it looks like we might be able to use this to get a preimage of a one-way function. So this one, we're trying to put it in every single place.
So y star is hardwired now?
Yeah, y star be hardwired, correct. Okay, so y star is just created in this way, but then it's hardwired from that point on. Okay, and in particular, what I want to do is that coming out of this work, I want to leave the proof program intact. In particular, the proof program should not know R. Otherwise, that would mess up my final strategy. Okay, so let's see how we can do this. What we're going to do is again go through 2 to the n length hybrids. Okay, and here we're not going to worry about whether they're true or false. And let me just try to give you a quick high-level overview on how, let's say, one of them works. So let's say I'm doing for a single statement x. I'm trying to move it from the way it was here to putting in this logic. Okay? Okay, so in hybrid 0, it's going to be doing the check like we have it here. The first thing I'm going to do, it's going to be a combination of an obfuscation plus punctuable PRF step here, is we're going to check if z is equal to t for random t. So we're going to use punctuable PRF to put that in here. And we're, here it's going to actually execute this step, we're going to have to temporarily puncture the proof program, and it's going to be important that the proof program would never use one of that off-path key of logic. So this is where I'm using the fact that I have it only doing it on off-path things the proof program wouldn't do. Okay, next what I can do is I can just say, well, t is equal to some t prime XOR r, right? And I can change this check using IO into the following check here, right? Just substitution, essentially. Is that, okay, Rachel, okay, the concern. Okay, so that's from obfuscation again. The next thing I'm going to do is from obfuscation, and I'm just going to apply the injective one-way function to both sides. So I apply the injective one-way function to here, I get y star by definition, and here I apply it. Now here, this is another obfuscation step. These should all be 2 to the negative n times negligible, by the way, because I need to do it a lot of times. Here, this is where it's important that the function's injective. If the function weren't injective, what I'm saying would be false, right? They wouldn't be functionally equivalent. Is that all right? Okay, and then let's see, what did I do here? Oh, and here I just do the punctuable PRF to make t prime equal to this, and then I do obfuscation again to unpuncture it and make it whole, both the verification program and making the proof program whole again. Okay, so this would be just for one statement. Do something like this. Here I went into, I kind of did a couple combo things here, but like what we saw before. Okay, any questions on any of these steps? Okay, so I have to do this for every single one. Okay, so once this is done, I can finish. I can essentially, hopefully, just finish it off. Imagine an attacker that wins now in our game. Remember, the attacker has to win off path. Well, if the attacker gives me, I can do a reduction where the reduction knows everything except the preimage of the one-way function, right? It creates the obfuscation itself, just is given y star, and it's searching for that r where f of r is equal to y star. Well, when the attacker gives you some z where this holds, all you need to do is take z, XOR it with this thing which you know the key for, and now you have the preimage of the one-way function. Okay? So here we're able to see a way of actually, with complexity leveraging, putting this challenge at every single place. So we didn't need to know it ahead of time. Okay? Any questions here? And I think we'll see this, I think along the way we answered these questions about putting in one-way functions, injective one-way functions in the proof, even though we didn't see them in the construction. Yeah, so you kind of had space for the injective one-way function. Okay, one last little bit to tie off. I promised you a pure I/O approach, which meant normal one-way functions, not necessarily injective one-way functions, so there's a little small disconnect there. Let me just say we can get around this. First of all, one answer to this is that there was this work in 2015 which showed I/O plus one-way functions gives you injective one-way functions. So that's one way to say we're just done. We actually took a little bit of a different route in doing it to get a little bit of a lighter weight approach. So what we actually did was we sort of built it's not known how to get injective one-way functions from one-way functions, but we actually showed that you could do it with inefficient sampling. So here I'm thinking of a one-way function a little differently as I have a sample that creates a challenge and then verify like you can give an answer for it. And we actually created one where from one-way functions where you can do it except for the sampling procedure takes exponential amount of time. Now you might think, well, that stinks, right? Why would I want to have an exponential time algorithm? It actually is okay though because it's not used in the construction. It's only used in the proof. And what you can actually do is if your proof steps, you assume security against non-uniform adversaries or if adversaries given a vice, what you can do is just put that sampling into the device itself. Okay? Yeah?
Maybe a different route is that if you have a very hard one-way function, like with close to optimal hardness, then if you compose it with pairwise independent hash function, it becomes injective. And then using the result overhaul and Alex that we heard about yesterday, you can build from IO in one-way function, you can build such an exponentially, like optimally hard one-way function. So if you take an optimally hard one-way function, compose it with pairwise independent, it's a more complex route, but it's easy given other results.
Okay, yeah, I'll have to look into that a little bit more afterwards. The one way I'll say that, okay, so it's only needed in proof, and the one thing I think which might be useful later on is in the future, there have been a couple other instances where you can have a primitive that does not appear in the construction, but appears in a proof. And in addition to obfuscation, you can kind of imagine this happening. I think not just imagine, there have been a few cases where it's happened in fully homomorphic encryption, like object just appears in the proof, even though not in the construction. Also garbled circuits. Perhaps there's some other things I'm not thinking off the top of your head. So maybe later on down the line, people will be happy that we did it this way. Like if you happen to need an injective one-way function in one of these things, maybe it will just happen to work out for you. Okay, great. So one thing I did say, so this talk is focused on this line of work of getting SNARGs from indistinguishable obfuscation. Should say there's been many works on succinct, not just the ones I'm talking about here, on succinct non-interactive proofs. I won't have like things like BARGs have been popular in the literature recently, even before that, the techniques leading up to that. I'll just mention a few other works. I'm sure I'm skipping over a lot that are important. So one of them has been getting SNARGs from propositional proofs. And I looked at the schedule. It looks like we'll be hearing a decent amount about propositional proofs over the rest of today. There was this, in addition, they did other things too, but they also observed that for designated I think this came up in a question perhaps, for designated verifier proofs, it's already adaptively, the 2014 was already adaptively sound without that one-way function in there. We also showed some work at how to adaptively batch SNARGs, and then I think there are some things on universal SNARGs. And if one of your favorite works isn't up there, I apologize. I think there's, I'm sure many things that I actually missed. Before doing questions, I'll just turn off and say, I think the takeaway lesson, there's a couple takeaway lessons I came from here. I don't consider myself really a proof person. I work on encryption systems a little bit more, but it's kind of this, using IO for proofs is sort of a way to work on proofs without using, I think, the tools like SumCheck or PCBs, whatever, which I guess is convenient for me a little bit. Like you can actually make progress on it. Indeed, like we didn't even we tried to get NISIX and we accidentally got SNARGs along the way. I think the other thing that that's kind of an interesting question is this kind of in the end of the line? I know some of these other works are desperately trying to, okay, can we get SNARGs from LWE or something like that? It's not clear to me that there's like the next exact step for this work, right? We have, okay, you should get obfuscation from other assumptions. That would be great. But that's not really a, you're not really building off of that to do that. You're just trying a separate line of work. So I thought this was ending a little bit, but then I think that there's some other directions that where you would hope that some ideas from here could possibly work, but it's not clear how to do them. Actually, some people approached me with them, and I thought, okay, this is done, but then there was kind of like a new challenge, and so I still think that there could be things to do in this type of regime. Okay, great. That's it. Any questions? Oh, Elaine. Yeah.
Do you think it's possible to get rid of the sub-exponential? Like, is there any barrier or?
Well, I think so. There's a separation result by Daniel Wicks and Craig Zhandry and Daniel Wicks, and it's a neat thing, essentially showing that if your common reference string is small, that there's no black. Okay, I'm gonna not state it correctly. No black box proof of doing it, and they say for both the proof of polynomial and sub-exponential hardness. Maybe there's some caveat about whether you can have a mix of it, wasn't quite covered. I think one thing that maybe, I say this in a good way, so it's a really great result, but I think people may have, maybe one reason that we didn't do adaptive security earlier, is I think people maybe overread into it. In that they're like, when you first think of like, can you do adaptive security? They said, oh, Zhandry is about adaptively secure proofs, so that's why we got the selective one early, or non-adaptive one earlier, and later on we couldn't do adaptive, right? So I kind of, number one, I think the way I approached it, it was almost, I think it was a nice result, but I just kind of put it out of my head, like, don't believe it. And I think that's sometimes the right way to deal with these impossibility results is not to think about them too much. So I think maybe ignoring it was one of my contributions. But I don't mean that in a bad way. But I do think people overread into it because there were two reasons why it didn't apply to the early work: the adaptive security and the common reference string length. And so if you eliminate one of the two, it still doesn't apply, right? Like in order for Zhandry to apply, you would have to have a short common reference string, and it would have to be adaptively secure. If I'm willing to have one common reference string, it just doesn't apply, right? So again, if Rachel, you look. Reflect.
So that doesn't rule out having a long common reference string, but building it from polynomial hardness.
I don't think it does. Now, honestly, I really don't know whether you can do it. It seems to be challenging. It seems that you would need to go through the statements and realize. Yeah, I guess the short answer is I don't know. It doesn't rule it out, but I don't maybe have more insights to give you on that.
Isn't your reduction strong enough to decide the underlying language?
It is. It is indeed.
That's the whole point how you get around Zhandry, right?
Yeah. So she's saying, could there be a different way to do it where we didn't do that, essentially? And the answer is, I don't think it's like on the cusp of our knowledge right now, but I don't want to claim, step beyond that. Let's say.
So you overcame it. You're saying the CRS. So what? The way you overcame it is long CRS, or which one?
It's the same thing, right? It's the same thing, right? In some sense.
Complexity leveraging.
Complexity leveraging implies long CRS.
Okay.
Yeah. The questions of long CRS alone is enough. But I thought Zhandry applies it for long CRS. As long as adaptive proof is
It
very
implies
short.
if you don't use it says you need to use complexity leveraging, and that seems to apply.
Yeah, complexity leveraging is more crucial than the CRS length.
Yes.
Yeah.
So yeah, and again, I do appreciate these results for understanding stuff, but sometimes I do think, and again, I mean it in the right way, that you can almost psych yourself out of going after a problem by, a positive result you can just see with the reduction. Any of these, it's really, any of these impossibility results, there's so many caveats, and it's really hard to do you want to write another thing where you do sub-exponential plus polynomial combination? It seems like a lot of work just to pull it out.
Yeah, I'm curious. Do you have any high level? It seems like there's a couple steps to getting down to the pure I/O approach, and then do you have any high level takeaways of maybe new ways of thinking about functional PRFs that might be useful for other problems? How do you think? I guess psychologically, it took a while to get to here, right? Is there any
the pure I/O versus the number theory?
Yeah, I don't know. If you want to use I/O for other stuff, is there a nugget you can take from this that might be useful?
It's a good question. Yeah, it was weird because I think we actually talked about over dinner or something. It was a good, it was a good dinner. It was one of these things where it was weird. At first to me it seemed oh, you really need number theory, and then then you really didn't. it was one. I guess, it'd be interesting to try other things which seem to need, I think one of the ones was, I don't have a great answer for you now. It could be good to try some things out, maybe if you don't even get a new result. So one interesting result from I/O was getting, I think it was probabilistic I/O, gave you fully homomorphic encryption. And I think it really had two results. One was jumping from leveled to full, and one was just getting leveled homomorphic encryption to begin with. And in that case, you could get it from DDH, but it actually didn't work with learning with error. Now we happen to have learning with error directly for fully homomorphic encryption. But I think a good problem to try out, if you're interested in exploring it, is try to get that from learning with error. Just get the learning with error, forget the other ways of doing it from learning with error, and just try to do it. And this is one of these things I think maybe we don't explore enough is, could I try to do something where I don't get a new theorem statement? Like I just want a new technique for doing things and try to learn from there. I think that would be, sorry, I don't have a better answer for your question, but yeah. Yeah, I think it's a good question though. I should think about it more.
It feels like there's some sort of like this self-randomizability building strategy that a single challenge is embedded in like every possible
yeah, I mean,
kind of like a little abstract, little primitive.
Maybe that's a good answer to the question. Maybe we could actually define re-randomizable one-way functions and build them from injective. Maybe there's some definition of re-randomizable that we could build from I/O plus injective one-way functions or something like that. I didn't bother. That might be true. Like, yeah, we sort of, yeah. Another way of looking at it is we actually just did do re-randomizable one-way functions from I/O. Yeah.
Siri was saying you can get it. You
Sorry,
were
can you
saying
say again what
you
you
can
said?
get it from LW.
No, I said because you can get FHE from LW.
Yeah. Okay, so I think, sorry, let me answer Rachel since she has this. Well. So maybe we'll do one at a time, really quick. I can't be everything everywhere all at once. And so I think Rachel's question was, maybe one way she was saying is that perhaps what we did was do re-randomizable one-way functions from injective one-way. Yeah, re-randomizable one-way functions from injective one-way functions plus I/O. Yeah, it might be possible just to recast this in that way a little bit. I think. Well, we'll have to double check some of that.
Does that imply like some kind of collision hash functions?
It shouldn't. I think that would be a problem because we don't know how to do collision resistant.
Re-randomizable encryption, I don't think it's known to imply collision resistance.
Yeah.
So re-randomizable one-way functions. The first two papers that you had, they imply instance compression, which does imply, or some kind of instance compression, which implies CRH.
Okay.
The third paper does not.
Okay. I see. So maybe it's like some variant of re-random, like.
Yeah, maybe.
Yeah, we'll have to. I guess you can try it and see what happens. I think is this. It's probably fair to like try to see if you can come out with some abstraction that looks like re-randomizable one-way functions, or how much it looks like it. It's fair enough. Okay. Great. Okay. Thank you. Sorry, I didn't mean to cut you off.
Yeah, that was a great talk. Very clear.
Okay, cool. Thank you.